Maximum speed, unprecedented power, outstanding performance on the water. It all begins with a high-performance engine, an engine that affords the advanced Tec-Neeks advantage. Through experience and experimentation, tedious research, and an ongoing quest for the best, the advanced Tec-Neeks professionals have developed some of the most sophisticated and dynamic custom jet ski engines available anywhere in the world. How do they do it? You're about to find out as the Advanced Tec-Neeks team shares insight and information that has elevated their product to world-class status. It all happens right here at the Advanced Tec-Neeks facility in Mesa, Arizona.
Hi, my name is Charlie Lawler. I'm the owner-operator of Advanced Tec-Neeks. For the past 25 years, I have been involved in the motorcycle industry as a motorcycle mechanic, as a professional motorcycle racer, and for the past few years I've been involved in teaching at the Motorcycle Mechanics Institute. During recent years, I have focused much of my experience and energies on the development of high-performance jet ski engines. In this program, my staff and I are going to give you an over-the-shoulder look at what we do to make our 440 and 550 engines premier products that have proven themselves over and over again. As you can imagine, building a high-performance engine isn't a one-man job. My staff, Tom Birch and Dave Simon, play crucial roles in the machining processes that have brought our engines to the leading edge. Before we jump right in on the engine building and the machining processes, let's take a look at what we're working with. The crankcases are the foundation of the jet ski. Some important areas that we want to check on the jet ski engine are: one, the sealing surfaces between the crankcases, in these areas right here. The other thing that we want to check is the base gasket surfaces. We want to make sure that these are flat. The way we check this is by using a surface plate and a feelers gauge. What we do is we put the plate, the crankcases on the surface plate, and we start checking it with a feelers gauge. And we just go through here in various areas and check to see if the cases are warped. If the cases are warped, they have to be discarded. And we would do the same with the top surface. The next thing we want to do with the crankcases is we want to check where the main bearings ride. If these areas here are shattered, the cases also have to be discarded. And you'd want to check it on your top cases to see if they've been shattered. The cylinder cases come as a match set, so that's the way you would purchase them. After the cases have been checked and the sealing surfaces on the crankcase halves and the base gaskets have been checked, we recommend using chromoly studs. The reasons we recommend chromoly studs is for two reasons. One, because of the compression ratios that they have, a chromoly stud doesn't stretch. This is what we want because if we had a stud stretch, we could have a base gasket blowout or a head gasket blowout. Okay. If you're going to install a stroker crankshaft, the top cases have to be modified. Where they have to be modified is in this area right here. There's a ridge that we have to take a porting tool to grind out. And we take this out. On some of the stroker cranks, we also have to notch where the rods would go in these areas right here. Before we go on to assembling the motor, it's important that you take a tap and run it through and check the condition of the threads that hold both the cases together and these studs. Now let's take a look at crankshafts. On jet skis, they have two types of crankshafts for the 440 550s. One is known as the full circle crank. The other crankshaft is known as the T-web crank. Then the crankshafts are broke down into two more areas yet. The full circle crank also came out with a stub like this, as you can notice right there. This crankshaft was found on the early 400s and 440s. This crankshaft, like this, can be stroked, but it cannot be rebuilt due to non-availability of rod pins. The T-web crank came into jet skis from 1982 on. This crank is also available as known as a non-rebuildable crank. The way we can tell a non-rebuildable crankshaft is by the orange bands on the main bearings. This crank can be stroked, but I recommend stroking rebuildable crankshafts. Since we're talking about crankshafts and stroker cranks, a lot of people ask, what is a stroker crank? A stroker crank is a crank where we take and disassemble it. We take where the big end rod pin is, we plug it. Then we modify or change the stroke in this area here. We move the stroke up so many millimeters. These crankshafts work well in recreational and racing jet skis. A lot of people ask, which is a better crankshaft, a T-web or a full circle? One, as you can see, a full circle crank is a lot heavier than a T-web crank. So this would give us a lot more torque in a motor. The other thing about a full circle crank is that it stuffs the crankcases where we can build more crankcase pressures. As we can see, the T-web crank, one, is lighter, and the things that are nice about a light crankshaft is we can make a motor wind a lot quicker. So it's really rider's preference on which crankshaft to go with. And we stroke both. The other thing that we offer for jet skis is known as the Pro X crank. A Pro X crank is a crankshaft where we take and make the crankshaft's halves out of 4130 chromoly. And we install the axles in this 4130 chromoly. These are very expensive crankshafts. Another variation that we do to the stroker crankshafts is we also offer crank seals, where we can seal the inner cases with, instead of using the Labra seal, which comes standard on a jet ski crank, we have crank seals that are available. Another thing that we can do to crankshafts is we can take and have them heat treated. The problem with jet ski cranks is that their Rockwell harnesses is about rated at a 30, which is pretty low on the scale. With a heat treating process, we can bring them up to about a 40-45, which is machinable. What's nice about that, it makes the crankshaft so it doesn't flex. We also offer many rod combinations for stroker cranks, recreational cranks, and super modified crankshafts. The stock rod for a jet ski looks like this. As you can see, we have one slot here for oiling, no oiling holes on the top. On our performance rod kits that we offer, we have an oiling hole here, an oiling hole here, and then we have 3 oiling holes here, here, and here. Another rod that we offer is what they call the TZ Yamaha 250 rod. This rod is found in the Yamaha road racing motorcycles that is capable of turning 14,000 RPMs. Some neat advantages of this rod is, one, it's 8 grams lighter. As you can see, it's built a lot better. It's what a lot of the pro riders are using in their jet skis right now. That's about it on crankshafts. We're going to go in the back here now, and I'm going to show you how to disassemble a crankshaft. This is where we assemble and disassemble crankshafts. We try to use assembly jigs as much as possible to assemble the crankshafts. Right now, I'm going to disassemble a 440 T-web crank. We use a press here. We use a 10-ton press to disassemble the crankshaft. After we get the crankshaft disassembled, we'll take it and bead blast it and go through other procedures of inspection. After we get done bead blasting the crankshaft, we take and put this on a lathe and we polish the areas where the main bearings and the crankshaft seals are. After we've got this done and it passes all of our inspections, the next thing we do is we index the crankshaft. Indexing is a process that will help us when we go to assemble the crankshaft It'll also help us for phasing the crankshaft in. Phasing is the firing order on the crankshaft. We set this in our indexing tool like this. Basically like this. And then we have an indexing mark right here, which will help us on the assembly of the crankshaft. Next, we'll go over and assemble this crankshaft. The most important thing we have to do now is phase the crankshaft in. And what we do there is we have a jigging device to phase the crankshaft in. First, we put these inner main bearings on. Okay, put our Labra seal on here, put our bearing here, and go like this. Put this device like this. We use all assembly jigs for assembling the crankshaft. Just like this. And we assemble it accordingly. After this is done, we put the rod in. Now the crankshaft is phased within 180 degrees. After the crankshaft has been assembled, the next thing we have to do is true it. There's a procedure of truing the crankshaft, and after it's trued, we use Kawasaki specifications for checking the runouts. We check the runout here on the inside, see what kind of runout we have on the inside bearings. Then we come out here to the outside bearings, check the runout, and we adjust accordingly. We try to ship all of our crankshafts out within 1/1000ths runout. Okay, the crankshaft is true. Now we'll go and assemble the motor. Okay, now we're ready to install the crankshaft into the crankcases. First thing you want to do is make sure you put the locator rings on both ends of the crankshaft, then install the crank seals. It's very important here that we put a little grease on the seal's lips right here and slide them on accordingly. Do the same thing here. Grease them up. Okay. Now we're ready to put the crankshaft into the crankcases. Make sure that you get the right end. The magneto end always goes to this end of the crankcases. Make sure the crank seals are installed, and then we put the crankshaft into the cases, making sure that the dowel pin lines up with the hole in the cases. After you've got that all lined up, shake the Labra seal, making sure that it's in place. Then, make sure the seals are in their places. Make sure that the snap ring is in place, and rotate the crankshaft. Make sure that there's no bind. Next, take and dab some grease inside here with we use a Q-tip, and we put grease in this area here. This just gives the seal a lot longer life. After that's done, we use 3-bond 1211 sealer on the cases. What we do is we put the 3-bond on these sealing surfaces here. After you've got that on liberally, then you're ready to put the cases together. Install the crankcase bolts, torque to 18 foot-pounds, and follow your Kawasaki manual on the rest of the lower end assembly. Next thing that we want to talk about is pistons in jet skis. There are two types of pistons that are available for jet skis. There's the OEM, which is a cast piston, which comes standard in the jet skis. There are many aftermarket manufacturers that are making these besides Kawasaki. And the other piston that's available for jet skis is the Wiseco piston, which is made in the United States. It is a forged piston, and it's the piston that we recommend being used in our racing jet skis. We prefer the Wiseco forged piston. Reasons why: one is the narrow ring gap. Two, the lightweight of the pistons. They come as a balanced set. The other thing we like about them is the ductility of the piston. It's a matter of preference. We'll use whatever the customer wants or recommends. Okay, next thing is for boring the cylinder out is some of the equipment that we use. The equipment that we use is, our shop is set up in the metric system, and we use digital metric mics. Also, we use a dial bore gauge. This is a device for checking piston to piston cylinder wall clearances, and also for checking cylinder taper. Next, we'll show you how to set up a cylinder on a boring bar. But before we can bore a cylinder, we have to check it out to see if it's worth being bored. The things that we want to take in concern here is: one, the head gasket surfaces, the base gasket surfaces, and the general condition of the cylinder, and if she's worth boring. After the cylinder has been inspected, then we go over here and we bore the cylinders. Here we've got a 300 jet ski cylinder in the process of being bored. We use an AMI boring bar, and we bore the cylinder to within 3 or 4 thousandths, and then we hone the rest out. Before we hone the cylinder, though, we have to use a torque plate. This is a 440, 550 cylinder set up with a torque plate. Torque plate basically is a device that we took a used cylinder head and bored a hole in it and then installed it onto the cylinder. The reason we use torque plates is so that when the motor thinks that it's been assembled, so that we can take and make sure there's no distortion in the motor when we go to bore and hone it out. This way we can have a straight bore when the motor is assembled. After we got the torque plates installed, then we install the cylinder into the servo-equipped honing machine, which is a precision honing machine that we use here at Advanced Tec-Neeks. After the cylinder is secure, we just turn the machine on like this, and it's all done by automation. We go like that. We use the Sun & double wiper honing stones instead of the single to give us a lot truer bore. After the cylinder's been bored, we remove the cylinder from the honing machine, we wash it with solvent and soap and water, and then we're ready to install the cylinder on the motor. Okay, next thing we're going to teach you is how to use a degree wheel to degree a motor in. A degree wheel is a device that the engineers use to design the port timing of the engine. A lot of people get confused after reading a Kawasaki manual what they're talking about by port duration. Port duration means the time that the intake or the exhaust port or the scavenge port are open. I'll take the cylinder here and try to explain to you what we're trying to do here. The first port I'm going to explain to you is the exhaust port. What we're trying to do there is we're going to try to find out how long this port is going to be open. I'm going to show you from a side view here, having the piston come down and going back up. That's what the duration is of a piston, of the exhaust port. The next port that I want to talk to you about is the transfer port. In the Kawasaki manual, they're known as scavenger ports. They're the ports that are on the side of the motor. The way we figure the durations there is from when the port just starts to open, goes all the way down until it's open. So these two ports, the way what determines their duration is the top of the piston. The next port that we're concerned with is the intake port. And what controls that is the piston skirt, going up and down like that. This is your intake duration. Now when we look at a Kawasaki manual, it kind of confuses people. What it says in the manual is that the cylinder port timing for the exhaust port is supposed to be 82.3 degrees before bottom dead center and then 82.3 degrees after bottom dead center. Now the way we talk port duration is with the big number. What I mean by the big number is we take 82.3 and add it, or take it times 2, and you'll come up with 164.6. Now, if you take the transfer ports, which are called scavenger ports in the Kawasaki manual, it's 58 degrees. Take that times 2 and it gives us 116 degrees worth of duration. And the 74.3 for the intake ports gives us 148.6. So remember, when you're figuring duration, you take the duration degrees provided in the manual times 2. Okay, now it's time to hook the degree wheel up to the engine. Basically all you do is you just slip it over the magneto side and put a nut on the end here to affix it to the crankshaft. The next thing is, if the motor is not a stroker motor, you'll just install the base gaskets, which this particular motor is. We'll just be using the base gaskets. Now if this was a stroker motor, there's 2 ways that we can go. One, we can use a stroker plate that will go in place of the base gasket, or we'll use base gaskets and we'll cut the top of the piston to alleviate the stroker problem of lengthening the stroke. If we do this, to determine how much we cut off the piston, we have to put the pistons on now and then rotate the motor through and see how much these poke up and then lathe off the top. Most pistons we have to take 28 to 30 thousandths off. After we have the cylinder installed, next we put on the stationary pointer that we'll be using. Now we're ready to degree the motor in. Okay, let's do the transfer ports first. What we do is you just turn the cylinder down until the transfer ports are about to open. Then take your degree wheel and put her right here on top dead center. Okay. Now what we do is you just rotate the motor all the way down through the full duration of the ports being opened. Port is now just ready to close. Then you read what it says on the degree wheel. We come from here, from top dead center here, we've got 90, 100, 110, 115, 118 degrees. You'd want to write that down. The intake port, the way we do that is we come over here by the skirt, get it where she just starts to crack open, put the degree wheel here on top dead center, rotate it all the way through, full duration, then write down what it says. We've got 90, 110, 120, 130, 140, 150, it's 163 degrees. And you'd want to check that according to your manual. That's basically how we use a degree wheel. Okay, after you've verified the ports timing, now it's time to modify the ports to what you want to do. What we do is we use some Dicom and we put this in the cylinder walls. We put this up here on the top here on the transfer ports. What Dicom does is it makes it so that when we scribe the lines, we can see what we're going to be doing here. Okay. While we're letting that dry, let's just review something. Remember, the top of the piston dictates transfer port and the exhaust port duration. The piston skirt dictates the intake duration. Okay? After the Dicom is dried, we put the cylinder back on, and now we'll map out the ports. Okay. Remember, when we checked the ports before, it was 181 was our exhaust port duration. What we'll do now is put the motor up to, piston up to the top of the exhaust port. We'll zero it in. Rotate the motor through. We're going to change the exhaust ports to this to 185 degrees. We're at 181 now. We'll go 185. All right, now we're at 185 degrees, but what we want to do now is we don't want to use this mark because we've changed the ports by 4 degrees, so we'll go half that, so we'll back it off 2 degrees. So what we do here, you just back her off 2 degrees. Now we scribe the line in here like this. Okay, now we want to verify to make sure that we've got the line in the proper place. What we'll do now is put this up on top dead center again. Rotate the motor through. Bring the piston up to that scribe line. And we've got 185 degrees. You use the same procedure to do the transfer ports. Now let's do the intake ports. Now what we do here is we take, remember we use the piston skirt to determine our intake duration. All right, set the motor here. We'll put this on top dead center. Bring it back down there. Let's see what our readings are. We've got 90, 110, 120, 130, 140, 150, 160. It's 162 degrees. We want to put that to 165. The way we do that, we just rotate the motor to there, and then we back it off 1 degree. And you scribe the piston. Okay. Now you want to verify what you've done. Put the motor top dead center here. Rotate it. And we look at what we've got. And as you can see, we've got 165 degrees of intake duration. We've got the ports all mapped out. Now I'm going to turn it over to the person that does all the porting in our shop, Dave Simon.
Thanks, Charlie. I'm going to show you a couple tricks that I've learned in porting over the past couple years. Now on the jet skis here, there's 3 things that we want to keep in mind. The first thing you want to concern yourself is, what kind of power do you want? You want top end, do you want mid-range, or do you want low end? Now everybody calls here and they want it all. But now 2-stroke porting, the best you can do is 2 out of 3. On jet skis, there is a couple numbers where you can get a lot more mid-range and top end, and get a little bit more low end, although those numbers can't go out. See, the second thing that we want to keep in mind is don't overport. You can always take more out, but when you want to put more in, it gets tricky. The third thing we want to keep in mind is keep things equal between ports. To start off, keep transfer ports symmetrical between both sides. Make sure measurements are the same between the auxiliaries and the mains on each side in the same cylinder, and then make sure they're the same on the other cylinders they are on this one. Same on the intakes and the exhaust. That'll keep things running at optimum. Last but not least, use the best tools you can. These are some of the tools that I use here. This is the tool I use mainly for porting. I use this on the exhaust and the intake, and these are some of the bits that go with it. I also use these on the transfer passages themselves. This is the right angle 90-degree tool that you use for getting into the transfer ports. I usually use this through the top of the cylinder, grinding on the top of the ports like this and on the sides. Now these tools plug into a shaft that goes into an electric motor that I can control with my foot, so I can do the best job I can as far as concentrating on the ports. And I can control the speed with my foot. A lot of you may have air grinders out there, and they're real hard to control. They turn a lot of RPMs and they're real quick. Jet ski passengers are small, so it's real easy for that tool to start flopping around making a mess out of your ports. So just take it easy, sit down and use a low RPM and do a good job. Now, these are the cutting tools themselves, and these right here are sanding rolls. I use these on a mandrel to finish up the ports and make them look nice. This is one of my main tools here. This is the divider. I use this with a metric rule, like this, to make sure I get the right width, to make sure ports are the same between cylinders. As far as porting themselves, the first port we'll start with is the intake port. Let me give you a word of advice. If you want to increase intake duration, take it off the bottoms of the pistons instead of the ports. If you don't like it, it's a lot cheaper and easier to replace pistons than it is to replace the cylinder or try to put material back into it. On the intake, there's two things we can do. We can widen it and we can lower it. Widen it increases our port mean area, and lowering it increases our duration. The first thing I suggest is cut material off the bottoms of your pistons after you scribe the mark like Charlie showed you. Go out and ride it and see if you like it. If you like it and you want more, come back in. The next thing I suggest would be widening these ports instead of cutting more off the bottom. On a 550, about as far as you can go in width is 48 millimeters. The reason of that is because you'll cut into these stud holes here and here. The same on the exhaust. On a 440, the bore is smaller and the piston's also smaller, so we can't make it as wide. The reason that we can't is because since the piston is smaller, we run the risk of the piston coming out of the intake port. If we get it to the extremes where there's just a little bit of piston skirt on each side of the port, then we run the risk of snagging a piston skirt on the bottom of the port, and it's real easy to season that way also. No support. If we already cut the bottoms of our intakes, just go ahead and follow the stock design. It's already there. It's a good design. It meets with the intake track and it helps dump the gases right into the center, where it's lower right into the center here. When we're grinding with our tool, we'll want to grind first with this grinding bit here. Grind to about a ½ millimeter above your scribe mark. The reason we don't grind all the way to the mark is because we'll finish it up with a sanding roll here. Make a nice finish, and it's easy to control and helps us get both sides the same. The last thing we'll want to do on the intake port is chamfer the bottom of it slightly. The reason we chamfer it is because the bottom of the piston won't snag on the bottom of the intake port. It doesn't need a big chamfer. The smaller the better. The sharper the cutoff is there as the piston comes down, the snappier power you'll have right off the bottom. Now on the exhaust, the first thing I recommend is to widen them. When widening the exhaust, we don't have to be concerned about different widths for 440s and 550s. I recommend going 48 millimeters. That's a good size to go without having to worry about cutting into your stud holes here and here. After we get our width taken care of, let's go ahead and raise it up to the line we scribed. Again, follow the shape of the exhaust port. It's a good shape, a rounded shape. The reason we want that rounded shape is because as the piston's coming up and down, the ring is flexing in and out of that port. With a rounded shape, that'll give a ring a place to start, it's bulging out, and a path to follow as it comes back into the piston. That'll keep you from breaking rings. Now again, as we're cutting the intake port, we'll cut with this tool here, and we'll go down a ½ millimeter before the line and finish up with the sanding roll to make a nice smooth port. Make the ports the same between each other. You want to finish up with your dividers, making sure that each port is the same. Now one of the things you have to be concerned with on the exhaust ports is the water jacket right here and here. A lot of times people will cut up too far and they'll cut into this water jacket. That's real hard to fix, especially on cast iron. From what I found, 33 millimeters is the most you can cut between the top of the exhaust port and the top of the cylinder on a non-deck cylinder without going into the water jacket. Now the finishing stages of the exhaust port, a lot of people like to polish the exhaust port. From what I found, finishing up with a light sanding roll works just as well as polishing it. A small amount of water that blows back through the exhaust on a jet ski is enough to keep the carbon from building up. If it makes you feel better to polish, then go ahead and polish it. The last thing you want to keep in mind on the exhaust port is to put a good chamfer on it. Maybe you can see in here. Be sure and put a good chamfer on the top and on the sides and also on the bottom of the exhaust port, because the ring travels past the bottom. The last thing you want to do is have to worry about a ring snagging and blowing out your exhaust port. After your exhaust ports are taken care of, the last ports we have are the transfer ports. On transfer ports, one thing you want to keep in mind, if you're building a motor for optimum power, these passageways here, the passageways in the middle are about 20% bigger than the passageways on the outside to begin with from the factory. So the first thing that you want to do is cut material off the outsides to get them equaled up to the insides. Now you'll never know if they flow exactly the same without a flow bench, which we'll show you later on. After you've got them matched pretty well evenly up, or so you think, go ahead and go inside and reshape them to a shape you desire. And I finish them up with a skinny sanding roll like this on a long mandrel to make sure there's no big bumps in there and they have a nice smooth flow. After we get that taken care of, we want to direct our attention to the transfer windows themselves. Maybe you can get a good shot here, here and here. We'll go in with the 90-degree tool, like I showed you before, coming in from the top. Sit down and take your time, run this at a middle RPM, and grind the tops of your ports up to the line that you've scribed. This bit doesn't have big teeth on it, so you don't have to worry about making a chattery mess. And besides, they don't build sanding rolls this small anyhow, so do a good job and make it nice and smooth. After you get the tops finished to where you want, go in and clean up the sides. A couple things you want to be concerned with on the sides. First, after you get this cleaned up into a shape you want, measure it so you can make all the ports exactly the same. The other thing you want to be concerned with is this cylinder wall right between the big port and the small port. Keep it as thick as possible for ring support. And on these big transfers, I don't do much as far as reshaping and widening. On the small transfers, I take the side of the transfer closest to the intake right here, and I usually widen that out a bit. The width I go is about 27 on the big transfers and 19 millimeters on the small transfers. Make sure they're all equaled up. The last thing we have to concern ourselves with is, let me get something to point with here, is the angle right in here between the transfer passage itself and the window. We're going to want to make that angle the same angle that's on the piston top. That means that'll vary between 440s and 550s. That angle will be somewhat flatter on a 440 than a 550 for optimum power. One last thing to be concerned with on the transfer ports is the transfer port passage divider right here. You can see that it has a nice radius on it from the factory. We're going to want to keep that radius. A lot of times you'll get cylinders back that you've had people port for you or seen that have a knife edge on that. The reason we don't want to knife edge that is because your crankshaft's rotating in this direction, which means the gases come in like this and come around and come back up at an angle. If they hit a knife edge, they're going to want to stuff themselves into this back port right here. With the radius edge, they can divide themselves evenly into each port. Alright, this is a flow bench, what I told you about before. This machine is used for the measurement of air through an orifice. This is mainly used for 4 strokes flowing heads, but we can also use it for 2 strokes. The reason we use it for 2 strokes is, one, to equal up or to check the measurement of airflow through the transfer passages so we can get them the same from one side to the other. Like I was telling you about before, how the middles flow more than the outsides stock. After we get those cut more on the outsides, we can go ahead and check them with the flow bench. Then if we want to redesign them some more, after we get those cut, we can come back and check them on the flow bench. It makes more of a difference than you think, getting the outsides matched up with the insides and one cylinder to the other cylinder. The other reason they're used on 2 strokes is for measuring airflows for things like carburetors, intake manifolds, etc. The way this is set up here, we have this top case sitting on the flow bench, sealed with clay on the inside and the outside to keep it from sucking air. We have the cylinder set on with the base gasket underneath, sealed with grease to keep that from sucking air. We've got a piston in place held by a rod and a bolt and this plate to keep it from moving. We've got the inside transfer port sealed off on the bottom with the clay, so the only thing that'll be flowing there is these outside transfers. We'll flow these outside transfers first, and then after you get done with that, you would take the cylinder off, block up the outside transfers, and check the insides. Now this here is called a manometer. This measures inches of water, which measures the amount of air that flows through this machine. On a 2-stroke, we use 7 inches of water, which is the same amount of air pressure that flows through transfer ports. On exhaust ports we use 15, and on intake ports we use 10. This right here is a flow meter from 0 to 100. The most accurate range on this flow meter is from 70 to 100. These here are orifices that measure airflow coming into the machine, and this chart here, plus charts in a book that comes with this helps you get your final readings. We're not concerned with final readings right now. The main things we're concerned with is that 7 inches of water, does the outside transfers flow the same as the inside transfers on this scale? If you want to get everything right down to the wire, then you can go into correction factors and temperature factors and things like that, but it's not going to make much of a difference on the same day. So right now, I'll turn this on. It's sort of loud, and we'll see how much it measures from here. We're not going to take this off and change it for matters of time, but first we'll turn it on here. As you notice, we ran this up to 7 inches of water and waited for a while because it sank back down, so we adjusted the knob till it stayed at 7 inches of water. And then we read our reading over here, and we ended up with a reading of 71.5. That's the reading we're concerned with right now. After we write that reading down, we'll take this off and check these inside transfers, and hopefully they'll follow the same. If not, we'll port accordingly. After we read all through and everything matched up, we got a race winner. Now that we've got the rest of our motor taken care of, the last thing we have to worry about is the compression ratio, the proper way to adjust it, where it's at, and where we want it. The way we adjust our compression ratio is the assembled method using fluid, which is an alcohol and dicam mix, to see how much fluid our combustion chamber holds with the piston at top dead center and the motor assembled. The reason we do it this way is because this is how the engineers did it when they first built this motor, and we believe this is the proper way to do it. The first thing we do is assemble the motor with the piston rings in place. We take our piston and set it about a quarter of a ways down from top dead center. Get a finger full of grease and smear it around the top of the cylinder like this. The reason we do this is to help seal the rings and to keep the dicam alcohol mix from seeping by the rings while we're checking it and giving us a false reading. Now run your piston up to top dead center, with the rings catching the grease on the way. Wipe off the excess grease so it doesn't give you a false reading. The compression ratios that we shoot for are between 12:1 and 14.5:1. Alright, now we want to install our head using the head gasket also, so everything is just like it would be if it was running. Use 4 bolts on each of the long studs. We tighten down our other bolts. Don't worry about torquing them. Just get them snug so they can't leak. And we use a syringe like this with accurate measurements on it. These measurements are in cc's. We fill it up to 30 cc's. Your head shouldn't be holding more than 30 cc's or it's not going to run too well. With our piston at top dead center, we put our syringe in the spark plug hole. Press down, filling up the combustion chamber with the fluid. We're going to want to run the fluid right in the middle of the spark plug hole. So as we get to the bottom of the spark plug hole, we're going to rock the crankshaft, making sure, while we're watching the fluid, to make sure that the piston's at top dead center. Now we see it's at top dead center. Look at our syringe and see how much we've used. We used 29.5 of the cc's that we started out with. Now to figure out our true compression ratio, the way I do this is by first finding my bore size on the cylinder that I filled up. The way you find your bore size is you first need to know what your piston size is, and second you need to know what your stroke size is. The formula for figuring out bore size is bore times stroke times 0.7854. On this particular motor, I have a 68mm bore and a 60mm stroke times 0.7854 gives me a displacement of 217 cc's on one cylinder. I now need to take that 217 cc's and I need to add it to my 29.5 cc's, which was the volume of alcohol I used to fill up my combustion chamber. I then take that number and divide it by my 29.5 cc's, and I get an adjusted compression ratio of 8.3 to 1. After we figured out what our compression ratio is and have an idea of where we want it, we have to figure out how to get it there. The first thing you do is disassemble the motor, take off the head. One of the main tricks in jet skiing is to surface the head. On stock heads, there's a big lip between the squish band area right here and the surface of the head right here. It's a 60 thousandths lip. That's normal on any jet ski, is to see a jet ski with a milled head. Normally they'll take off anywhere to 50 to 60 thousandths. You don't want to cut into your squish band right here. However, if you do, this head can be placed on a mill and the squish band can be cut back out at this angle or at a different angle. That's some of the tricks they also use for high performance. Different angles and different combustion chamber shapes. Now, after we've got it cut, we want to put it back on the motor and fluid check it again. See where it's at. If it ends up that you need more, you can always cut more off the head, or a better thing to do on a motor with a stock stroke is cut some off the top of the cylinder. You also have a 60 thousandths deck height between the top of the piston edge, the top dead center, and the top of the cylinder. I would recommend cutting material off the cylinder if you're going to run a stock stroke instead of cutting more of the head, just because of losing water volume in the head. Another way to get around keeping water volume in the head and adding compression, on a stock head while you still have your big clearance, one of the things to do is to weld up your squish band and recut it out with a mill. That way you'll take up your squish band area by filling it up with a weld, and you'll recut it out and you'll add material to the head, thereby increasing your compression ratio. These shapes can be completely altered by welding, milling, and lathe work. The last check we make on our race motor assembly is to check the clearance between the piston at top dead center and the squish band of the head. We do this by cutting a piece of solder the size of the bore and placing it on the piston as so. We then run our piston down a little bit below top dead center so we can bolt the head in place. We're concerned with the clearance between the piston and top dead center and this squish band right here. We want to keep that clearance at 35 thousandths or more, but hopefully as close to 35 thousandths as possible for maximum power. The reason it has to be that much is because of loose fitting pistons and jet ski cylinders. After we have our solder in place, we bolt our head on, like so, using the 4 long studs again. We tighten our head down again. After we get our head tightened down, we run our crankshaft through its bases so our piston goes to top dead center and back down again. If you've cut off the top of your cylinder, you may feel the solder hit. On this one, there's so much clearance, it's all stock, that you can't feel the solder hit. Then we take off our head again. Now this motor is set at 60 thousandths, but it also has a low compression ratio. So that means we can mill off our head, tighten up our squish band, and get our compression up at the same time. Compression ratios and squish bands somewhat go hand in hand. After you've made sure your flywheel and shaft are in good condition, install your stator plate. Be sure to use at least a blue Loctite grade on the stator plate bolts. If anything can come loose on a jet ski, it will. And that's one of the last things you want to have come loose. Before we assemble our flywheel, it's a good idea to have something like this dynamically balanced. It's 8 pounds worth of metal flying around on that crankshaft. The closer it is to true and being balanced, the easier it is on your crankshaft, the funner it is to ride your jet ski due to less vibration. That's about it for stock flywheels. The other kind of flywheels there's aluminum flywheels, and there's KV ignitions, where they take a stock flywheel like this, remove the magnets, which is the majority of the weight, Usually turn down the outsides and drill some holes in them to make them lighter. If you're racing, it may be one of the things you'd like to consider. It puts a lot more low and snap into the motor, and it makes it rev a lot quicker. I use one on mine, and I just love it to death. As far as ignition timing goes, anywhere from 22 degrees to 28 degrees is normal on a jet ski. As far as what you should run, it all depends on what your compression ratio is at and the design of your head. It's something that you have to sit down and figure out where it's at and go to the leg and adjust it from there. I can't tell you which is best for you because it all depends on every motor and each stroke, as far as 60 millimeter stock, 64 and 65 millimeters with your strokers. All will change your timing and all require different timing adjustments. After we set the timing at where we think it should be, we want to go ahead and assemble our motor with our flywheel. Always be sure and use a new flywheel washer. These things like break and a new one's 89 cents worth of insurance. But your flywheel nut's not going to come off and you'll lose the flywheel. After we get that installed, we want to put our flywheel nut on. We want to torque our flywheel nut down to at least 115 pounds, which is what Kawasaki recommends. The best way I suggest that you hold your flywheel is either with a Kawasaki flywheel puller, which holds here, here, and here, or by taking off the head and putting a coiled up piece of rope or tubing under your piston. When you're rotating the flywheel to where the nut's turning and your piston gets to top dead center, that rope will hold your piston from turning past top dead center. That's a good way to tighten down your nut with no strain on the crankshaft. If you try holding it from the back of the crankshaft, 125 pounds is a lot of torque on that crankshaft, and there's a good chance it'll twist right in the centers. That's the last thing you want. Now after we've got our flywheel on, the only thing left is to put our manifolds on and the rest of our motor together. Take your time, do a good job, use new gaskets and sealers, and you'll be rewarded with a great summer jet skiing. Now here's Charlie to tell us what's in store for you customers of Advanced Tec-Neeks as far as high performance goes in the future.
Thanks, Dave. Well, that's about all we can tell you about how to build a 440-550 jet ski motor. I hope this information is very valuable to you. If you're having a problem with this, feel free to call us or else send us your motor and we can build it for you. Let's talk about some of the things that are in the future for Advanced Tec-Neeks. One of the new things that we're working on is a temperature control unit for jet skis. This will be available for all of the jet ski models. What this is it's a device that controls the temperature of the waters. Advantages, we'll be able to run tighter piston clearances. We'll be able to adjust our carburetors a lot better. This here is a prototype that I have in my hand. This device here is a thermostat that tells them what the water temperatures are. The tests that we've had good results. This will be available in January of '89. Another thing that we've got is slide pumper carburetors that we're working with. Another thing that's on the drawing boards are variable exhaust ports, which so far have been quite successful. Another thing that we're working on is another video on how to tune the hulls on jet skis. I want to thank you for watching this program. I want to talk a little bit about legislation. Right now, there's lots of laws that are coming down in Arizona where they're trying to restrict jet skis. I think that we as individuals that ride jet skis should try to follow the boating rules, and we see people that are offending and breaking the rules to let them know that they're hurting our sport. I enjoy the sport and I hope you enjoy it. I think that we'll have a fun 1989 year with jet skis. Thank you.
Maximum speed, unprecedented power, outstanding performance on the water. It all begins with the Advanced Tec-Neeks Advantage.